Hi, today we're going over section 1.3, which is using reasoning to find a counterexample to a conjecture. So essentially today we are going to use logic to try to disprove conjectures. So we'll try to find things that don't work with various stated conjectures. So we can invalidate a conjecture by finding a contradiction. So as soon as we find something that does not work with a conjecture, it is invalidated. So it's no longer useful. So we have this example, 6, 12, 10, 50. There's a conjecture, all but one of the vowels A, E, I, O, and U are used to spell numbers. Gather evidence to support or deny this conjecture. So right now we're saying that one vowel is essentially not used in the spelling of numbers. So what we can do to try to invalidate this is see if we can use all letters. So first letter here is an A. So we'll try to think of a number that has an A in it. Okay, so if we have the number 1,000, it has an A. It also has an O. It has a U. So now we just need to find a number that has an E in it and one that has an I in it. So for example, 10 has an E in it and 6 has an I in it. So we've invalidated this by showing that all vowels are actually used in the spelling of numbers. There's not one that isn't used. So when we provide something that invalidates a conjecture, that's known as a counterexample. So it's an example that goes against the conjecture, hence why it is counter. So our next example, a student found an interesting numeric pattern. So if they took 1 times 8 plus 1, that gave them 9. If they took 12 times 8 plus 2, that gave them 98. They took 123 times 8 plus 3, they got 987. They took 1,234 times 8 plus 4, that gives us 9,876. So we can see that there's a pattern here. So we're starting at 1, then 1, 2, then 1, 2, 3, then 1, 2, 3, 4. And then the number that we add here would be our term that's right before the 8. So our ones term. So we had 1 here, so that's 1, 2 here, that's 2, 3 here, that's 3. And essentially it's creating this pattern where we're counting down from 9. Now they think this pattern will continue, so we'll try to find a counterexample. So we will try some of these, see if this pattern continues. So we have 1, 2, 3, 4, 5 times 8 plus 5. If we calculate that, we get 98,765. So that's still following that pattern. We'll try one more. So 1, 2, 3, 4, 5, 6. So 123,456 times 8 plus 6 gives us 987,654. So the pattern seems to be holding up. So what we want to do in situations like this is then try to look for areas where we think it may struggle. So, for example, what happens when the number that we're adding onto here becomes larger than 1 digit? So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9, we have 10 times 8 plus 10. If we calculate that, that gives us 9, 8, 7, 6, 5, 4, 3, 1, 2. So that doesn't follow the pattern, but just to be safe, to see if maybe the pattern is it loops back to, say, a 0 here instead of a 10, we'll try that. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 times 8 plus 0. That gives us 9, 8, 7, 6, 5, 4, 3, 1, 2, 0. So that also doesn't follow the pattern. So we can say that these are counterexamples. So we found a spot where the pattern no longer holds. Now, if we want to follow that same, want to continue using that same conjecture, we'd have to say that it works for numbers 1 through 9 as we put them in here. It does not work when that number that we are adding here becomes double digits. So some key points: if a counterexample is found, the conjecture is considered to be disproven. So at that point, one has to come up with a new conjecture if they wish to follow through with it, or abandon it entirely. If you cannot find a counterexample, that does not necessarily mean that one does not exist. It's just more likely that the conjecture is true.